One of the holy grails of physics, certainly for theoretical physics, has been the idea of unification, unifying our theories into one theory of everything. This is the history of unification of physics. It starts with the very first two disparate phenomena that were unified by Isaac Newton. Newton supposedly sits under the apple tree on his mother's farm. Whether or not the apple actually fell on his head, I don't know. Essentially, what he realized was that the invisible force that pulls the apple down to the ground is exactly the same force as the one that keeps the moon in orbit around the Earth and the Earth in orbit around the sun. That is obvious to us now, that's gravity, but back then there was no reason to think that the laws of physics that govern the behavior of objects here on Earth would be the same laws that govern the motion of heavenly bodies. Newton was the first person to unify those two rather very different phenomena into one with his law of gravity. The equation that we all learn at school, the force is the product of the two masses divided by the square of the distance between them. That was the first big step in our journey of unification. Middle of the 19th century, James Clerk Maxwell had been following Michael Faraday's experiments with the electricity and magnets, messing with them, and seeing what induced magnetic fields and so on. Maxwell developed the theory that showed that electricity and magnetism are part of the same more general field called the electromagnetic field. So, Maxwell unified electricity and magnetism, heat and energy, thermodynamics, so that combined with statistical mechanics. The theory you learn at school was called the kinetic theory, that things like pressure and temperature are really just vibrations or oscillations of molecules in a gas. That was unified together into what we now call thermodynamics. Beginning of the 20th century, Einstein unified space and time and gave us in 1905 his special theory of relativity. That's the theory that tells us E equals mc squared. It's the theory that says nothing can go faster than light. About 1915, Einstein unifies the special relativity. He broadens it to give a more general theory, general relativity. Because he gives us a new picture of Newton's law of gravity. It's not an invisible rubber band that pulls masses together. Einstein's picture of gravity is the curvature of spacetime. His general relativity theory, many regard as the most beautiful theory in physics. It combines his special theory with Newtonian gravity. Of course, general relativity then leads on to another whole new field of science, cosmology, which talks about the evolution, size, shape, and behavior of the properties of the entire universe. The existence of atoms is probably only proved mathematically, in fact, by Einstein in 1905. By the end of the first decade of the 20th century, Ernest Rutherford has looked inside atoms for the first time and discovered the atomic nucleus. Now, we hit the mid-1920s, we have quantum theory. That's first developed at the beginning of the 20th century by people like Max Planck, who says heat radiation is lumpy. Ultimately, it's made of tiny lumps of energy called quanta, as where the word quantum comes from in physics. Einstein and others developed their ideas, and by the 1920s we see the emergence of what we now call quantum mechanics. It's the theory that replaces Newton's mechanics, because down at the level of atoms the behavior of matter is very different, so it needs quantum mechanics to explain it. Late 1920s, quantum mechanics are then combined with special relativity. This is the work of the English physicist Paul Dirac, and we arrive at what we call quantum field theory. Quantum field theory then is combined with electromagnetism. Quantum field theory just with the electromagnetism gives us something called quantum electrodynamics. We have quantum mechanics applied to the atomic nucleus, and we understand that there are new forces inside the nucleus holding its constituents together, and those two forces are called the strong nuclear force and the weak nuclear force. Those two forces were added to the other two known forces at the time, electromagnetism and gravity, to give us the four forces that we know of in the universe. The strong nuclear force also is described by a quantum field theory to give us quantum chromodynamics. What about the weak nuclear force? That was then combined with quantum electrodynamics to give us an even more general theory called the electroweak theory. We arrive at the sort of the late 20th century, where we have three of the four forces of nature described by quantum field theories. We have quantum chromodynamics that describes the strong nuclear force, and the electroweak theory, which describes the electromagnetic force and the weak nuclear force together. These form what we call now the standard model of particle physics. So, the standard model is everything we know about the three forces of nature that can be described within the quantum realm. It may not be the end of the story. In fact, We're pretty sure it's not the end of the story, because we really like to combine the electroweak theory and quantum chromodynamics into one really solid theory, called a grand unified theory. We're not there yet, but the standard model of particle physics is pretty much everything we know now about the world of the very small. Remember, I left you with cosmology, which is the new theory from general relativity that gives us what we call the standard model of cosmology. Lambda is a quantity called the cosmological constant that crops up in Einstein's equations of general relativity, and CDM stands for cold dark matter. Because within our standard model of cosmology we know we have to include an explanation of dark matter and of course also dark energy. We don't really know entirely how dark matter and dark energy fit into the standard model of cosmology, because we don't really understand what their nature is. We don't understand what they're made of, but we've arrived from falling apples all the way down to statistical mechanics, all the different phenomena in the physical universe. We've got two models, the standard model of cosmology and the standard model of particle physics. What we really want to do is combine the two into a theory of everything, a theory which physicists refer to as quantum gravity. You can see where the name comes from, quantum mechanics and gravity, because cosmology essentially comes from Einstein's theory of relativity, which is a theory of gravity. It's the fourth force, what we don't yet know how to combine with the other three forces in the standard model of particle physics. My view is that thermodynamics is the third pillar of physics which we tend to forget about, and I think we're only going to arrive in the theory of quantum gravity when we understand how to fit thermodynamics into the picture as well. Likewise, there are new areas, so quantum mechanics has led to a whole new field called quantum information theory and quantum computing, and that may have some bearing on our final theory. Similarly, I've just added lots of our stuff where we're still trying to get our heads around nonlinear dynamics, complexity theory, non-equilibrium thermodynamics. There are missing ingredients, essentially, is what I'm trying to say before we can reach a theory of everything, and we don't know how far off that is. Where are we at the moment with candidates for a theory of everything? One of them represents what we call string theory, and that's the theory trying to unify the four forces of nature. And the other is a rival approach called loop quantum gravity, which is trying to quantize space and time themselves. Both come at this from different directions, but both are trying to achieve the same goal, to be the theory of everything. We don't yet know whether the string theory or loop quantum gravity is the true theory of everything.